which is concluding this morning's block, would be by Arno Amberla, Vice President Technology, Proventia. Arno has graduated from Tampere University of Technology in Finland. He has a degree in material science, and he's worked for 2 more years at the university as a researcher in combustion technology. And he joined Proventia in 2000 as the Vice President for Technology, and he has been recently responsible for Stage 5 emission control technology development for non-road applications, but is also working on still on on-highway systems, what I get from this CV here, including retrofit system development for trucks and buses. Okay, so we will see you with a presentation, Meeting Ultra-Low NOx Emissions from Future Non-Road Diesel Engines. The floor is yours.
Thank you very much.
Arno.
Good afternoon, ladies and gentlemen. As said, my presentation is also covering part of the topics discussed earlier in these 2 presentations, and shortly presenting what Proventia is, then going on mechanical designs on Stage 5 after-treatment systems, onboard diagnostics, discussing a little bit of sensor requirements, sensor placements, and also online monitoring system, which is close to SEMS, presented by TNO. Very briefly, Proventia, we are making emission control systems for OEMs and retrofits, and that is for engine manufacturers as well for vehicle machine manufacturers and for retrofits. Other business area is test solution, where we are doing container-sized test cells. Our activities cover engineering services of the after-treatment, all the testing validation on the product, and then eventually also manufacturing of the systems for Stage 5 and other emission requirements. So we do in-house performance emission testing, aging and durability testing of the systems, mechanical testing as well, corrosion testings. And on the test solution side, we can do container-sized test cells for diesel or other fuel cells or other fuel combustion engines, as well the whole drivetrain, including possible hybrid units in the drivetrain. Then going to Stage 5, state-of-the-art design and experience. The market drivers, they are the same, what was also mentioned by Mr. Joshi from Liebherr. So the fuel economy, cost efficiency of the systems. Right now, Stage 5 and China 4 is having a discussion of possible EGR dropout. That increases engine out NOx emissions, and therefore SCR has to have higher efficiency. Also, it's expected to have engine rated speed to drop down, also because of saving of fuel, and real-world emissions and in-use testing is going to be also in place on Stage 5, and therefore the actual emissions from engine has to be on low level in any use. Limited space and compact design, that is always the driver on non-road side. All the manufacturers are claiming that their application is the most difficult in terms of space. That is what we have heard, whether it's tractor, excavator, or whatever application, always the manufacturer says that their application is the most critical in terms of space. The high NOx reduction target is challenging. We have to inject more urea at low temperatures. Possible wall wetting leads to deposit formation on SCR. Hopefully, all the AdBlue or urea what is injected is converted into ammonia and be part of the SCR reactions. Many SCR catalysts can reach 99% NOx reduction efficiency at optimum conditions. Then it's a little bit of choice of manufacturer on which area and what temperature they are operating and what kind of catalyst they are going to choose. From SCR point of view, there are low temperature side and also the high temperature sides. It can be on the same application. It can be a seasonal machine. So on certain seasons it works at low temperatures, and certain seasons it works at high loads and very high temperature. The same system has to comply and be effective on both seasons and both engine load conditions. Same applies on the mass flow. It can be low mass flow or high mass flow depending on what the machine is actually doing, and therefore the system has to be designed to meet demands and targets on the both cases. On the SCR side, there are two main criteria we are dealing with. One is that the urea mixing at low temperature and the dosing should start below 200 degrees C. 170 degrees C is one example. It can be a little bit lower or a little bit higher, depending on what kind of engine it is and what kind of dosing strategy is chosen. And then at the SCR, flow characteristics should be at high level, meaning flow uniformity index about 0.96 and ammonia uniformity index about 0.98. That is tough target, and it should be met on many different load conditions. Here are two different examples, also suitable for the same engine side. It's either conventional EAT system on the left-hand side, where the DOC, DPF and SCR, they are a different box and mixer in between, or all-in-line after-treatment system on the right-hand side, where all the components are on the same axis, starting from DOC, DPF, injector and mixer section, as well as SCR, including typically slip catalyst. These both should meet the uniformity index targets, and for example on this inline concept, this can be a scalable system starting from substrate diameter of 7.5 inch up to 13 inch of diameter. Then it covers engines from 56 kilowatt up to about 300 kilowatt. And example on about 100 kilowatt engine, the diameter of substrate is 7.5 or 8.5, and external diameter of about 260 millimeters, including insulation, and keeping the total length below 1 meter. Or it can be a conventional but very flexible after-treatment system, where the SCR mixer and DPF, they are all standardized, but DOC inlet and SCR outlet parts are custom made for different applications, and there it becomes very flexible. It can be either fitted on top of the engine or located remotely from engine on different angles and positions. With a good mixer, either in the inline concept or on the standard one, we are using so-called super tornado mixer, where we have high dosing amounts, and in this case, over the dosing map, we have normalized as number one the injection alpha 1 values from engine side, and on the blue bars we can see the safety and the optimization margin on different engine points. That engine and that optimization margin can be utilized to change engine out baseline to higher fuel economy, or to start a little bit at lower temperature dosing, or making a little bit more compact system. So it depends on the application and customer requirements, different weighting of the benefit can be used. Another very important thing on the design is thermal management, as we are seeing idle operation and low temperature operation. Thermal management, so that the all heat is used on the catalytic reactions, is crucial. And for that, thermal insulation is a must on after-treatment components, but also it's possible to have it on engine components, including manifold and turbo. Basically, this improves fuel economy by the function that we don't have that much of heating functions from the engine side, and we are keeping all the heat in the right place for catalytic reactions. And on the other hand, we are also keeping the temperature at the engine room low, so that we don't have to have extra cooling to cool down the engine compartment. For this, we have a lot of data here, and starting from the simple pipe connection, we can see that benefit with insulated pipe is something between 5 to 10 degrees C, just over the pipe length, and the greatest benefit, so less heat loss, thermal loss, takes place at low load conditions, and that is when we have the most challenging conditions already in the beginning. Then we have here example of insulated manifold and turbo. Some graphs coming. This was tested at about 7-liter non-EGR engine and at very low power rating. So it was the most tricky condition on that engine what was available. It was stage 5 engine with active thermal management, but had the same calibration. And from the mass flow, we saw that during some operations, the engine had less heating functions with this insulation. That might have had effect on the fuel economy, but in this test it was not possible to find out that how much the fuel economy improvement was with insulation. At steady state conditions, the insulation gives benefit about 10 degrees C on the manifold and turbo insulation. So to sum up the previous slides, about 5 to 10 degrees C benefit from the connection pipes, we are summing up somewhere between 15 to 20 degrees C benefit from overall insulation. On the non-row transient cold cycle, it was seen that the benefit of insulation on the manifold and turbo was not having too much of a role in the beginning. So the heat mass, which was on the manifold and turbo, was playing the biggest role in the first sections. What was seen in the middle of the test cycle was that less active thermal management when the insulation was installed on the engine. One big advantage came from beginning of hot cycle, as after the 20 minutes of soak time, heat remains more in the manifold and turbo. So those components were hotter, and heating of the after treatment was faster, and resulting that the injection could be started earlier in the test cycle. On the hot non-road transient cycle, the NOx reduction was 99 plus and resulting 0.0206 grams per kilowatt hour and combined 0.2 grams per kilowatt hour. If that result is going to be improved further, it needs more function in the beginning of cold phases, especially on the cold start. Either it needs EGR, more close coupled design, or mass decrease, and the benefit is case depending whether it's beneficial to invest on those components or those methods or not. A bit surprisingly, the insulation had no or little influence on the cold NRTC NOx emissions, and that is partly because of the heating phase. There is no heat radiation taking place, and all the extra heat is used to warm up the components inside the insulation. But definitely easier control of hot cycle and faster dosing start, that was concluded with the insulation. Onboard diagnostics, to have this high ammonia uniformity index, it's needed to have some sort of validation method, and we are using ammonia scanner at the SCR outlet phase. That requires only 25 millimeters free space after the SCR surface, and if the SCR dosing is done at alpha 0.8 or 0.9, we can calculate NH3 using NOx values. And in many cases, and in these cases, we are using 25 different positions on the scanning, and they are equal on area what they are measuring at the outlet. This is example of inline concept. On the left-hand side, we saw that ammonia uniformity index was 0.996, having at alpha 0.9, which is good. But on the other hand, from the NOx out, we saw that there are areas of potential NOx sensor position having NOx 88 ppm or 130 ppm. So the variation, there was variation even at that high ammonia uniformity index. Average was 106 ppm on the surface. There are also another example of 0.998 uniformity index, but as we can see from the right-hand side graph, the conditions are not stable, and these results need to be rejected. So this concludes that the NOx sensor positioning has to be checked even on stage 5 and in any of those low emission cases. This can be done by comparison NOx sensor signals from reference sensor, which is located further downstream of the system, compared to the NOx sensor, test NOx sensor, which is close on the SCR. And it can be seen that in many cases some sort of mixer before outlet NOx sensor is needed to have it on representative values in all engine operation points. A bit on the emissions and its monitoring. Proventia is having a Procare Drive emission monitoring system. This gives real-time emission data transparently to operator. This is based on signals of vehicle sensors, and it doesn't replace the PEMS, and full location of NOx sensors gives inaccuracy to results. In generally, we have seen that this system gives always pessimistic results compared to PEMS. If PEMS is the real, then we are showing worse results than the real emissions are. This is web-based. We are sending all the information to cloud, and it allows machines' emissions to be reported reliably and daily. From the left corner we see hourly sum of NOx reduction values. Then on the top view we see a snapshot, or we can select any time of operation, and then we can go a little bit further down to see that how reliable the data is, and how all the data second by second, vehicle speed, operation, all the parameters we are getting from the canvas. But again, this is based on the sensors which are in the machine or vehicle, and we have to rely on those, and if they are incorrect, then this result is also partly incorrect. But this is very powerful tool for field test to reveal possible design and calibration errors before the systems go on serial production. It's also possible to check with two sensors difference between sensor signals. If there's a reference sensor located on position which gives average reading of NOx, so with a mixer or further downstream from the system. To sum up, meeting ultra-low emissions and also including stage 5, compact, flexible design of after-treatment system is needed. Thermal insulation plays more role. Also the thermal management on the engine side, but then it's a balance of CO2, where to put and how to get the CO2 benefit. SCR catalyst which is chosen has to have high usage, meaning ammonia uniformity index above 0.98. Good choice on the catalyst. There are different catalyst types available, and all they have good points and also perhaps also bad, not that good characteristics. Sensor positioning for accurate OBD plays a big role. Otherwise, the readings what are getting for the OBD, they could be somehow false. Thank you.